Hi, so what I wanted to do with this video was sort of follow up on last night's class. We got through a lot of the key concepts about why the central limit theorem is so important and how we use it for a lot of things, but I sort of stopped short of exactly explaining how you might apply that to some of these problems. So what I want to do here is a little video on solving some of the problems from your text. Just as a disclaimer, it is not my preference to do it using PowerPoint, but right now this is the only option I really have with the technology that I have. I would prefer to write it out for you, but I'm sort of stuck with PowerPoint, so we're going to go from there. So first thing we got to talk about is the terms that we have to use for all of this. So just like anything, you have to learn the language. The first thing that you've got to understand is that in most cases we're going to be using this X bar. That's the mean of the sample that we're talking about. It's the estimator of the entire population. And then we're also going to be working with the sample error, or the standard error as we call it. So when we do the sampling distribution, we are going to assume that we're taking a sample out that is every single sample that is chosen has an equal chance of being chosen, and the sampling distribution has some normal frequency. So those are important things to just know up front, and they apply more when you start using this with real data, because all of the stuff in the textbook is always going to fulfill all of these assumptions. So we define the variance of x, or the amount of variation we expect to be around x, at variance is sigma squared, whereas the standard deviation of x is going to be the square root of the variance. So just keep in mind that variance is not really all that useful to statisticians. The only useful tool it serves is that we can then get the standard deviation from it. So in that case it is useful, but variance in and of itself is not in the same unit as the problem, because it's the error squared. And then we've got the standard error here, and that's going to be sigma divided by the square root of n, and so that's where we get into the bit about the sample size actually mattering, etc. And the final formula that we're quite interested in and we're going to use a lot is going to be this z calculation. This is going to give us the probability that our event occurred as we have specified or not. Now we're going to move on to an example, and we're going to apply and use some of this. So here we have the example with the pizza shop. We're working in this pizza shop. On average, pizzas are 16 inches. And the standard deviation is 0.8. So we want to determine the standard error. So as you can see down here, I've got it calculated out. The standard error is going to be the standard deviation divided by the square root of n. So here we've got 0.8 divided by the square root of 2, because we have 2 pizzas in this first example. And then in the second one we have it divided by the square root of 4. So what this tells us is that when we have 2 pizzas for n, notice that our standard error is a little bit bigger than it is when we have 4 pizzas. So then what to do with something like that? This here you can see on this next slide. So what would be the probability that one randomly selected pizza would be 15.5 inches or greater? So you see the way I've got this set up here. The probability that whatever we're interested in is 15.5 inches or greater. So we plug the numbers into the equation, and you notice I put 15.5 here minus 16, and it's minus 16 because the mean of the pizzas was 16. And we divide this out. Now we divide in this case by just 0.8, and that's because in this one we only have one randomly selected pizza. There's another example that we're not going to actually do, but it has 4 randomly selected pizzas. So if you had 4 randomly selected pizzas, you'd have to have 0.8 divided by the square root of 4. But in this case we only have 1 right here. Notice the 1. So we have the 4 excuse me, we have the 1, and so we have just 0.8. Hold on a second here, my Z moved on me. All right, so now we divide that out, we get this 0.625, which means that this option occurring is 62% below the mean on the normal distribution. So I'm going to flip to another slide and I'll draw a normal distribution, and I'll sort of show you visually what this looks like. So you'll notice I put this handy little red line in here. So when we divide this out, we get this negative 0.625. We looked this up on the Z table and we get this 0.2643. So that means that we have a 26.43% chance of randomly selecting one pizza and having it be 15.5 inches or smaller. So it's this red line all the way back to the origin. So you can see here, what we're interested in is the space of the normal distribution that is accounted for in this red, between these red posts here. So this one all the way back to the origin. So the answer is 26.43%, but you can see that we've got 2.5%, 13.5%, and then some part of this 34%. So it does make some sense. Had the question been, what is the probability that one randomly selected pizza is 15.5 inches or greater, then the answer is going to be 1 minus this, or about 75%, because now we're interested in the red line moving forward. So it depends on how the question is asked. So how about we change this word here, greater, we'll change this to greater, or change this to less than, and we'll make it red so that we know that that corresponds with the red down there, and then we'll put a thing here, and then we'll put greater than, and we'll make this blue, and then I'll put a blue arrow for that. So now you can see I put the percentages as well. So if we're interested in from this red line back to here, it's about 25%. I kind of rounded a little bit. But if we're interested from this red line forward, it's 75%. So we have a 75% chance of getting a pizza that's 15.5 inches or larger, and we have a 25% chance of getting one that's 15.5 inches or smaller. So that makes pretty good sense. So now what I'd like you to do is pause the video and go into your textbook and try doing problem number 7.3. It's not a problem, it is a exercise in the book. And just do the same thing for, in the case of pulling 4 pizzas, and sort of talk yourself through it and make sure you understand it sort of the same way. And then once you're ready, hit play again, and we'll move on to doing the problem that involves Starbucks and there at the beginning. So in this problem, this is from the introductory case. They want to find out if the marketing campaign is what has influenced people to spend more money on iced coffee. So in this example, they've got the average originally being $4.18, but now we find people are spending $4.26. So we want to compute the probability that people are spending $4.26 just by happenstance. So we want the probability that X is greater than $4.26, and we do our calculation. And this one here, we've got to take the standard deviation and divide it by n. In this case, it's 50. I've gotten all this information from the problem. And what happens is we calculate this out. We get 0.67. That's what happens when you take 4.26, we divide by 4.18. But here you have to kind of pause and say, okay, so what are they asking? Because that depends on whether or not you need to do 1 minus or take the value or whatever. So we look up this number, we get 0.7486 off of the Z chart. But then the question is, how do we determine that? And basically we have a 75, what it's telling you is there's a 75% chance that somebody would spend $4.26 or less, and a 25% chance that somebody would spend $4.26 or more. So if we use the same normal distribution from the previous slide, we can mark off the same thing. So with this one, you can see I've sort of reversed it. The mean, instead of being 0, it would be 418. And then we're looking at 426. So 426 is going to be about right here. Not quite a full standard deviation. It would need to be $4.29. So it's about here. And my line's a little crooked, but you know, you get the idea. So we're interested in knowing the percentage chance that people are going to spend $4.26 or greater. Well, that's going to be 25%, and $4.26 or less, so that's from here all the way back, it's 75%. So a couple problems that you might want to try that use this is going to be problems 11, 22, 23, 24, 25. Those are all just practices that you could do. But I will write on Blackboard the ones that you might have to worry about having a quiz on. You might want to pause the video now and work on these, and then I'm going to finish off the video with doing the proportion of defects. Okay, so now we're going to talk about basically the same thing, except we're going to do it with a P estimator, because sometimes the numbers that we're working with are not necessarily continuous. So the P estimator lets us do the same sorts of calculations but with percentages. So here we have some very similar formulas to the ones that we did before with the continuous numbers, but the big difference is the standard deviation. So with the P estimators, we generally don't have a standard deviation of the population. Instead, we have to calculate it. I'm sorry, the standard error of the population, we have to calculate it, and we do this using this method right here. It's relatively straightforward, really. And this allows us a little more flexibility, really, in working with this type of data. So let's just move on to an example so I can kind of walk you through it and you can see what we're talking about. So in this example, what they've asked is the likelihood that the percentage of women and the percentage of teenage girls, and those are two separate things, might have been shifted as a result of the marketing. So in this particular case, before the campaign, the percentage of women who bought these iced coffees or whatever from Starbucks was 43%, and then after the marketing campaign it shifted to 46%. And then for the teenagers it was 21%, and it shifted to 34%. We've got an N of 30, and if we just pause for a minute and think about it, you can see that probably it's going to be more significant, as we use the term in statistics, for the teenage girls than it is for the women, because the shift is bigger. We go from 21% to 34%, and that's a pretty big shift. So let's go ahead then and calculate this out with a little picture, and so we can see how this happens. So here, this one here is calculated for the women. So we use the same formula as before. We've got whether or not we can say for sure that the percentage of women who drink iced coffees from Starbucks is 46% or not. So we fill in the numbers into the equations here, and we come up with this 46% minus 43%, and we're going to divide through by the standard error of P. And again, that's that same formula I just showed you. This gives us essentially standard error for a percentage as opposed to a continuous number. So we have this 0.43, you can see it here, and you multiply it out, and actually it doesn't show here, but if you were to just look at the denominator, so just the standard error, it should be 0.07. So essentially we're dividing 0.07 into this difference here, which is 0.03, and we should get about 0.42851, so we round that off to 0.43. So this tells us that the percentage chance that the percent of women that are drinking iced coffee from Starbucks, the chance that it would be greater than this 0.43 is 33%, because we calculate out the 1 minus the z value, right? Because once we do this division, we get this 0.43 number. We take 1 minus that, because we know that we're interested in this side of the distribution. And so we calculate the z score here, and we do that by taking the difference here, that's 0.03, and then when you were to calculate this bottom, the denominator, the standard error for p, we're going to get 0.07. So we divide 0.03 by 0.07 roughly, and we get actually 0.42851, and we're going to round that to 0.43. So this 0.43 is the z value we have to then look up on the z chart. So we look up our 0.43 on the z chart, and we get 0.66, or 66% of the way over to the first standard deviation is where our 0.46 falls. And what we're interested in knowing is the percentage chance of 46% or more people paying for their iced coffee at Starbucks. And so is this a significant difference, significant shift over from the mean, which was 41%. And so since there's a 33% chance that this happened by chance, we can't really say for sure that this marketing campaign has actually worked on women. However, we're going to now turn our attention to the kids, the teenage girls, and you can see that you're going to be way further out on the tails, and then we can assert that indeed our marketing campaign did indeed make a difference. Okay, so this is the last example I have here. Here we're talking about the girls, the teenage girls, and the question asks, they want to find out if the marketing is working on the teenage girls. And so originally they found 21% of teenage girls bought iced coffee, and now they went back and surveyed later, and they found 34% of the teenage girls bought Starbucks iced coffee. And so what they want to know is if observing a mean of 34% is something that observed or something that happened by chance, or if it actually happened as a result of the marketing. So we compute the z value by taking 34 minus 21, and then we're going to divide through by this standard deviation of the sample, and we're going to end up with 0.13 divided by 0.0576, and you get roughly 2.26. So that's 2 1/4, basically standard deviations beyond the mean is where this went ahead and put some numbers in here, and the standard deviation is about 0.0576, so I've kind of rounded these numbers. But basically we started at 21 was the middle, the mean, and then up to about 27, and then about 33 and about 38. So the number we're interested in here is 34, so it's just a little bit beyond the 33. So my lines are slightly off here, but you get the basic idea. And roughly what this calculation here tells us is we calculate this out, we get 2.26, we look that up on the z chart, and we're going to get 0.98881. So there's always some confusion about what does this number tell us. So roughly what it tells us is that our value that we're interested in, 34%, is 98% of the way across the normal distribution. So depending on how the question's asked, the answer is either going to be 98.81% or it's going to be 1.12%. So in this question it said what's the likelihood that this happened by chance? So the likelihood that we obtained a value of a mean after the marketing campaign of 34%, the likelihood of that happening by chance is 1.12. But the likelihood of obtaining a value of 34% or less, so all of these values from 34% all the way down to 0, now that would be 98%. So it has to do with the way the question's asked on whether or not you subtract it from 1 or you just use the value as it is. So, given all of this, I recommend that you do a few homework problems as I have them assigned, and practice this. I'll definitely have a short quiz for you on the homework this week coming up. I definitely recommend that you practice this stuff before next week, because it can be just hard to get your head around exactly how to do it. So hopefully this helps, and please let me know if anything is unclear or whatever. Alright, so thanks and have a great weekend. Bye.